Today we will talk about hypothesis tests for two means. Oftentimes we are interested in situations where we have to evaluate between two different treatment options, or maybe consider evaluating taking a treatment versus not taking a treatment, right? And understanding what the response to each of these situations is going to be. To proceed in either of these scenarios, we will need a hypothesis test involving population parameters that are coming from two different populations. This could also be the case where we are applying two different treatments to the same population. The goal for today is going to be working with hypothesis tests for two means. The assumptions that we are going to work with in this setting are going to be that we are having a random sample, which we will call capital X, and the elements of the random sample will be xi's. This is going to come from a population with mean mu1 and variance sigma 1 squared. We will have another random sample x1, y1, y2, y3 up to yn. This is a random sample coming from a population with mean mu2 and variance sigma 2 squared. We will also assume that the random samples x and y are independent of one another. In this setting, we can consider the sample means x bar and y bar. These are estimators for mu1 and mu2, and we are interested in estimating the difference between the parameters mu1 and mu2. This is the difference of the means. A basic estimator for the difference of the means is going to be x bar minus y bar. And we notice that the expected value of x bar minus y bar is exactly going to be mu1 minus mu2, which tells us that x bar minus y bar is an unbiased estimator for mu1 minus mu2. The variance for x bar minus y bar is easily calculated, and we get it to be variance of x bar plus the variance of y bar. It is sigma 1 squared divided by m plus sigma 2 squared divided by n. And the standard deviation is going to be the square root of the variance that we have just calculated. We will next talk about hypothesis tests for two means under two assumptions. The first assumption is going to be that the populations of interest are normally distributed, and that the variances sigma 1 squared and sigma 2 squared are known. In this setting, the test statistic of interest is going to be given by z equals x bar minus y bar minus mu1 minus mu2 divided by the square root of sigma 1 squared divided by m plus sigma 2 squared divided by n. This statistic has the standard normal distribution with mean mu1 minus mu2 and variance sigma 1 squared divided by m plus sigma 2 squared divided by n. The testing procedure is going to be as follows. We're going to note that the parameter of interest is the difference of means, that is mu1 minus mu2. The null value is going to be denoted by delta 0, and the null hypothesis is going to be that the difference of the means equals the null value delta 0. There are three alternative hypotheses in this case, that is mu1 minus mu2 not equal to delta 0. This is going to be the two-tailed test. Mu1 minus mu2 greater than delta 0. This is the upper tail test. And mu1 minus mu2 less than delta 0, which is going to be the lower tail test. We will then calculate our test statistic given the sample data. The test statistic is going to be calculated by small x bar minus small y bar minus mu1 minus mu2 divided by the square root of sigma 1 squared divided by m plus sigma 2 squared divided by n. We use the test statistic to calculate the p-value And the p-value calculation is going to depend on the alternative hypothesis. So if we are in the upper tail test, the p-value is going to be 1 minus phi of z. If we are in the lower tail test, the p-value is going to be phi of z. And if we are in the two tail test, the p-value is going to be 2 times 1 minus phi of absolute value of z. Phi z is the cumulative distribution function for the standard normal distribution. Once we have calculated our p-value, we can compare the p-value to the significance level alpha to get the test decision, which is going to be reject the null hypothesis if the p-value is less than equal to alpha, or fail to reject the null hypothesis if the p-value is bigger than alpha. Remember, there are two assumptions that we have to remind ourselves in this setting. The first being that the samples are coming from a normally distributed population, and the second being that we have information about the population variances sigma 1 squared and sigma 2 squared. No hypothesis test is complete without an analysis of its test errors in the test results. So the probability of making a type 1 error is the probability that we rejected the null hypothesis when the null hypothesis was true. This equals alpha, that is the significance level of the hypothesis test. The probability of making a type 2 error is the probability that you fail to reject the null hypothesis when the null hypothesis is false, with the true difference of means being equal to a delta prime. So whenever we are working with a type 2 error, remember we have to specify what the true difference of the means has to be equal to, and in this case we denote it by delta prime. The probability of making a type 2 error is going to be denoted as beta delta prime, and in each of the three different alternative hypotheses, we have three possibilities of making a type 2 error, and these probabilities are calculated as follows. Note that in the formulas here, the term sigma corresponds to the standard deviation for the random variable x bar minus y bar. Now, we can use the sample size to control the probability of the type 2 error, keeping all other parameters of the test fixed. And assuming that we have samples of equal size, that is, the sample x and sample y are of the same size, we can calculate a formula for the sample size for each of the three possible alternative hypotheses. Okay, so for example, in the setting of the two-tailed test, this relevant sample size that we will need to get a type 2 error to equal beta would be sigma 1 squared plus sigma 2 squared times z alpha over 2 plus z beta, the whole squared, the full divided by delta prime minus delta 0, the whole squared. We will finish up this video by talking about how we interpret test results. Suppose the null value equals 0 and that the test rejects the null hypothesis that the difference between the means is equal to 0. What this means is that there is a statistically significant difference between the means mu1 and mu2, or there is a statistically significant difference between the two treatments, treatment 1 and treatment 2, that give us means mu1 and mu2. The question of interest is, does that mean that the treatments corresponding to mu1 and mu2 are causing this difference that has been observed statistically? There are two settings over here. The first setting being in the setting of an observational study, and the second setting being a randomized controlled experiment. In observational study is a study where the objects used in the comparison are not assigned by the investigator, in the sense that this is coming out from data that has been collected prior to the investigator being involved with the experiment. On the other hand, the randomized controlled experiment, the investigator randomly assigns subjects to one of the two treatment options that are being studied. So, in the context of the observational study, H0 might have been rejected due to some underlying factors that had not been controlled. And as a result, we would have lower confidence in assuming causality. That is to say, that the statistically significant difference that was observed uh, in the test might not be caused by actual differences in the treatment options. On the other hand, when we are working with a randomized controlled experiment, because the investigator controls how the subjects are randomly assigned to the two treatment arms, we will have much higher confidence in the test results, in the sense that the observed statistical difference would be very likely be caused by the actual difference in the means or the treatments. Finally, to wrap up, we emphasize that experiments must be carefully designed with substantial thought given to, for example, developing clear assumptions and criteria for test subjects, figuring out proper sampling procedures, especially dealing with the question whether your test subjects' assignments are truly random, figuring out appropriate sample size to get desired error bounds, and finally, to document everything. It's very important in the context of being able to replicate a experiment by another independent investigator who might be interested in your results. We've kind of basically gone over hypothesis test today for the difference of two means. We'll talk more about hypothesis test for two population parameters over the course of the next few videos. But for now, this is all. Take care of yourselves, and I will see you around.